Now that we know exactly how to calculate probabilities of position and of momentum, it helps to take a quick step back to remember where we are, because now we can begin to open into new topics. So where we are, if you might recall, is we are right in the middle of our discussion on formal theory. And within this, what we are discussing is the topic of kinematics. And what we've just covered is the whole topic of quantum states, how we represent them with wave functions, and we've also now learned the connections between wave functions and probabilities. So our next topic, then, is how to deal. Now that we know probabilities, we really have, in some sense, everything that we need to know. But there's another set of topics that we can build upon this knowledge that is very useful, which is how to calculate quantum averages. Averages that appear in quantum mechanics. So we want to calculate, think about quantum averages, and in calculating quantum averages, the key mathematical superstructure that we are now going to build, a new piece of that superstructure, is something called operators. So you might ask yourself, well, we already know how to calculate probabilities, right? So for example, here is some probability distribution that I might have. I might compute for some quantum state. Some, probability density might look something like so. And you would say, well, at this point, I know then all there is to know. I know the outcomes of my experiments. Why would I want to consider quantum averages at all? Well, one of the nice things about averages, and which is why we want to study them, is that by looking at quantum averages, we can summarize. They summarize a lot of information in just a few numbers. And that's what makes averages very handy. So for example, if I have this probability distribution, we might be interested in, well, what typical value of x could we expect to see in our experiment? Well, the answer to that, of course, is that's just the average of x. We also might be very concerned with the uncertainty in x, the width of this distribution. Now, previously when we talked about Heisenberg, we just sort of, made a judgment call as to what we would call the width of a distribution. But now that we have proper probabilities in a mathematical framework, we can give a precise definition so that then you can actually prove very precisely the formal statement of the Heisenberg uncertainty principle that we had discussed earlier in the course. Now you can actually prove it, and that will be something that you do on one of your assignments. Now, the strict mathematical meanings that we can do proofs of delta x, the uncertainty is literally defined as the standard deviation of the corresponding probability distribution. And you will recall that the standard deviation is defined as the square root of the variance, and the variance is the average of the square of the variable minus the square of the average of the variable. So once again, another key summary piece of information about our distribution can be calculated provided we know how to calculate averages. So this is what we are going to begin to consider. Now, there are lots of averages out there to learn how to calculate, so I'm going to begin with a specific example. We're going to ask how to calculate the average of position in quantum mechanics and the average of the momentum. How would we calculate these? So let's start with the position. Now, formally speaking, if I think about position, if I wanted to average this, what I would do is I would carry out a series of measurements, right, of locations of my particle, and you know what those measurements will do, right? They build up these histograms that we like to think about. And then what you're going to do is you're going to sum up all the different x values that you get and multiply them by x, and then add up all the values of x you get, and then divide by the total number. Another way to do this is to actually group things by histogram. You can find out all the particles that land in a given histogram. We know their value of x. So we can take the total number that land in a given histogram. That is just the probability that you land in your range dx, right? That's the total number, basically, that land in there. You multiply by their x. And then when we divide by the total number, that in essence is what makes for our probability distribution being normalized. So this really is just the standard expression actually in probability for calculating the average of anything. It's all the possible values times the probability of their appearing. Now, in quantum mechanics, we know something else, right? We know that that probability in x is calculated as the magnitude of psi squared, but as we've been saying, it's always better, as we will see, to write things in the form of psi star psi. So let's write our integral using that form for p. So it's dx psi star of x, and I'm going to write things in a special form, and you'll see the motivation for this as we develop further into more complex averages. I'm going to write psi, and then I have to remember to multiply by x, excuse me. To do that, I'm though going to write things in just a slightly different order, x times psi of x. Now, part of my motivation for doing this is that notice now I could define this as some new kind of a function. I'm going to call that function a phi of x. And I do that because then you'll notice what I have is really something exactly back into the form of an inner product. This would be then the inner product of psi star, right? So that goes in the bra part, times this new function phi, and then integrating over all possible values of x. So I could write it this way, or another piece of notation I could use is I could say, okay, I'm going to take psi star, right? And then I'm going to integrate it against x times psi. So this actually is how I prefer to write the expression. So that is what we would integrate up to calculate the average of x. The meaning of this, of course, is just the expression that you see here. Very good. So if I have my state specifier psi, I can immediately calculate the average of x using this expression. So that's for the x position. Let's think a little bit about momentum. So at first, this story is going to be very similar, right? So to get the average momentum, the basic probabilistic definition of average is I integrate over all possibilities times the probability of finding those possibilities times then the value of what I'm averaging when I land in a particular bin of wave vector k. Now what I'm averaging, notice, is the momentum. So what I need to put here actually is the value for the momentum, but the momentum I know is directly related to k. So what I should actually put here is h bar times k. Next, we know we can follow the same pattern as before. P tilde of k, of course, is we want to write it as psi tilde of k times psi tilde. That would be the proper form. So this will become integral dk. And once again, I'm going to split my psi stars apart. It's just multiplication. There's nothing really mysterious. It's really just sort of to make things a little more artful at present. H bar k times psi tilde of k. And I hope you can see, and we can skip a few steps now. We're getting used to this. This then would be the inner product between psi tilde with then h bar k times psi tilde. And that's how I would calculate the average of momentum. I'll put a nice underline on that one. Actually, maybe we'll put boxes on these. These are very handy formulas to have. Okay, great. So far, so good. And you can imagine certainly doing the same thing for any observable O. In fact, let's try that. If I just had any observable O, I hope you can see very quickly it will become the integral over all values of O times their probabilities, which I always like to write as a bar for a typical observable times O. And then this P is going to turn into psi star bar psi bar. And then if we rearrange the expression, it will become psi bar inner product with O times psi bar. And that's how I would calculate a generic average.